Well, my dear student, now we are going to talk about symmetric molecule. Okay, symmetric molecule. So we are going to learn about symmetric molecule. You have to remember a molecule is symmetric when it will contain at least one of the symmetry elements. At least one of the symmetry. So what are the symmetry elements? What are the symmetry elements? So number one, plane of symmetry. Plane of symmetry. Plane of symmetry. Okay, plane of symmetry. Number two, center of symmetry. Number three, alternating axis of symmetry. Alternating axis of symmetry. So you have to learn, you have to know about the every symmetry elements in your syllabus. There will only two, that plane of symmetry and center of symmetry. So you have to know about the examples, about the structure, about the molecules which contains plane of symmetry or sigma plane, plane of symmetry or sigma plane. Another name of plane of symmetry is sigma plane. So let us take an example, that is tartaric acid. So structure is something like that, COOH. This is a carbon center, this is also a carbon center, and there is also COOH. And this carbon contain H and OH, this carbon also contain H and OH. Okay, if we divide this from this plane, then we will get the if it is an imaginary plane, that bisects the molecule, and each half are mirror image of each other, and they are mirror image, you can convert this like this. Okay, and they will be the mirror image of each other. Okay, so this molecule contains a sigma plane or plane of symmetry. This molecule contains, so name of this compound is mesotartaric acid. Name of the compound is mesotartaric. So mesotartaric acid contain a plane of symmetry. Okay, plane of symmetry. Well, another example is alpha Traxxalic acid, which contains a center of symmetry of center of inversion, I center of symmetry or I center. So what is the structure of the alpha Traxxalic acid? Let's draw. Suppose that there is a plane, okay, center of symmetry. We are going to find out the center of symmetry or center of inversion, I. Then this is sigma plane, and this is called center of symmetry is called I. Okay, I means center of inversion. Now suppose that the molecule is this. There is COOH, here is H, here is H, here is C6H5, here is H, here is COOH, and here is C6H5 group, and here is H. Now suppose that it is a center of symmetry. Okay, it is a center of symmetry, and from this center of symmetry, in the same distance, there is a COOH atoms, group of atoms, and in opposite direction there is also a COOH. There is also from this side there is also a phenyl group. From this side there is also a C6H5 group. In this way, there is also a H. Okay, so this center is called what? This center is called I, center of inversion. So the molecule which contain this center of I or sigma plane, they are called symmetric molecule. They are generally optically inactive. Symmetric molecules, the molecules which are symmetric, they are generally optically inactive. Okay, they are generally optically, well, I'm writing this, optically inactive. So these two molecules are example of optically inactive. So mesotartaric acid is optically inactive. But plus tartaric acid, what is plus tartaric acid? You have to see about the plus tartaric acid. Mesotartaric is optically inactive, but plus tartaric acid is not optically inactive. They are optically active. they are optically active because there are asymmetric carbon atom. There is no symmetry elements. So we are going to draw the structure of plus tartaric acid. So what is plus tartaric acid? Like this, COOH, this is carbon, there is also COOH, and there is HOH, and here it is OHH. So these two, carbon 2 and carbon 3, carbon at the position of 2, carbon at the position of 3, they are both chiral center. So this molecule is optically active. Okay, let us take another example of asymmetric carbon atom, okay, which show optical activity. Like suppose that the molecule is C, double bond C. This contain H and Cl, this contain H and Cl. The name of this compound is 1,3-dichloropropadiene. And if you take the mirror image, the mirror image will also be superimposable with each other. Okay, so here it is, H will be here. Is just convert this like this. So H will be here, Cl will be here, and this HCl will be on that side. Okay, and these two molecules A and B both are superimposable with each other. So they are optically active. ओके, ठीक है. तो हमने देखा मेसो टार्टरिक एसिड जो है दैट इज ऑप्टिकली इनएक्टिव, और द कंपाउंड विच कंटेन any one elements of the symmetry like plane of symmetry, like center of symmetry, they are generally optically inactive. And which is enantiomer, that means which contains a chiral molecule, which contain chiral carbon atom, they are generally optically active. Okay, optically active. So you have learnt about enantiomer, meso compound, and if we take the another examples, then we will see that what is diastereomers. Okay, so if you take the tartaric acid, plus tartaric acid, COOH, here it is H, here it is OH, here it is OH, here it is H, and if we take the mirror image, then it will be something like this. COOH will be here, this OH will be in this side, this H will be in this side, this H will be this side, and this OH will be this side. So this is A and this is B. So both of them are enantiomer. We know about this enantiomer. But what is diastereomer? So diastereomer will be like this. If you take the meso compound, mesotartaric acid, what is mesotartaric acid? COOH, HOH. So what will be its mirror image? Will be like this, COOH, and in both side there will be OH, and in this side there will be H. Suppose that CD. So you can say this CD are enantiomer, Okay, now you can call AC as diastereomer, because they are not mirror image of each other. Okay, AC, AD diastereomer होगा, and BC, BD, they will also diastereomer. Okay, because they are not mirror image of each other. AC, AD, BC, BD, there will be 4 pair of diastereomer. Okay, now you will learn about the calculation of the number of optically active isomers. So let us take an example. Examples of 3-bromopentan 2-ol. 3-bromopentan 2-ol. Let us take an example. One compound is 3-bromopentan 2-ol. So draw the structure of it. Bromopentan, so there will be 5 carbon atom, and 2 position में ol है तो OH होगा, 3 position में bromo means Br होगा. So there will be CH3, here will be CH2, here will be 1H, here will be 1H, and that will be CH3. So its structure, if we draw its structure, if you draw its structure, there will be suppose that it is a C2H5 group. You can write this as C2H5. So the structure will be something like this: CH3 upor mein, that's CH3, okay, that's CH3, then CHOH, okay. So you can write this like this, and in this carbon, suppose it is 1, it is 2, it is 3, and this is also a group, that is C2H5, that will be in the last position, okay. And this carbon 3 will contain H and Br, okay, H and Br. So this is the compound, and this is the structure, Fischer projection formula of this compound, okay. And there is two dissimilar chiral carbon. This is C2 and this is C3. Both are chiral carbon atom, but they are dissimilar. Because they do not contain the same type of atoms. So these two are dissimilar chiral carbon center. These two chiral center are dissimilar because they are not same. Dissimilar, okay, dissimilar. For dissimilar, the number of optically active isomers, the formula is 2 to the power n. N means, what is n? N means number of chiral center. So here the number of chiral center, equal to 2. So n equal to 2. So it will be 2 square equal to 4. So there will be total 4, and there will be total 4 optical isomers, optically active isomers, okay. In this compound there will be 4 optically active isomers. So where the dissimilar chiral carbon atom will be present, the number of optically active isomer will be the 2 to the power n, where n is the number of chiral center. So you can find out the number of optically active isomers which contains dissimilar chiral carbon atom will be like this. If you take the another example, that is 2,3-dibromobutane. Let us write the name: 2,3-dibromobutane. Okay, another example. 2,3-dibromobutane. Butane means 4 carbon are there. 2,3-dibromo. So here will be Br, here will be Br, here will be CH3, here will be H, here will be H, here will be CH3. So the structure is something like that. So if it is CH3 and this is also CH3, this contain H, this contain Br, this contain H, this contain Br. So here also carbon 2 is chiral center, carbon 3 is also a chiral center, but they are same, not dissimilar, and they contain even number of chiral center, okay. So for even number of chiral center, the formula will be 2 to the power n minus 1. 2 to the power n minus 1 will be the number of optical isomer, okay. Will be the number of optical isomers. So 2 to the power, here there is n ka value equal to 2, because there is 2 chiral carbon center. So 2 to the power 2 minus 1 equal to 2 to the power 1 equal to 2. So the number of optical isomer equal to 2. And here it is also, you can also find out the number of meso compound, number of meso isomers of this compound. So the formula for that will be 2 to the power n minus 2 upon 2. So here it will be 2 to the power n means 2 minus 2 upon 2, that is 2 to the power 0. 2 to the power 0 equal to 1. 2 to the power 0 equal to 1. So the number of meso isomer will be 1, and the number of optically active isomers will be 2. So this is the formula for optically active isomer. And this is the 2 to the power n minus 2 upon 2 is the formula of number of meso compounds. Okay. And if it is the odd number of chiral center, if you take the example of 3-bromopentane 2,4-diol, 3-bromopentane and 2,4-diol. So the structure will be like this. There will be three chiral carbon center, that is odd number, n equal to 3. Here n equal to 3. The structure will be like this: CH3, CH3 H OH H Br OH H. So for this compound, the number of optically active isomer, number of optically active isomer, the formula will be 2 to the power n minus 1 minus 2 to the power n minus 1 upon 2. So here n equal to 3. So the number of optically active isomer will be 2 to the power 3 minus 1 minus 2 to the power 3 minus 1 upon 2. So here will be 2 to the power 1 minus here will be 2 to the power 1. Okay, equal to 2 to the power 1. Right. So it will be 2 to the power 2. 3 minus 1 equal to 2. So 4 minus 2. So 2. Number of optical isomer will be 2. And for mesoisomers, what will be the number of mesoisomers? The formula is 2 to the power n minus 1 upon 2. 2 to the power minus n minus 1 upon 2. 2 to the power n minus 1 upon 2. So there will be 2 to the power 3 minus 1 upon 2 equal to 2 to the power 1 equal to 2. There will also be 2. Okay. So optically, we know that mesoisomers are optically inactive. Mesoisomers are optically inactive. So here the number of optically inactive isomers will be 2, and optically active isomers will also be 2. So these are the formula. By this formula you can calculate the number of mesoisomers and number of optically active isomers for three different types of molecules, which contain dissimilar chiral carbon, even number of chiral carbon, and odd number of chiral carbon. Okay, thank you. So this is optical isomer is finished. Okay.